Okay, everybody, glad you could be here. This is going to discuss agglomeration 3, or actually it's pressure agglomeration. Anyway, here's some questions, although I don't know how much you want to pay attention to questions. The sources of this material is Peach and Book of Powder Science and Technology. That's a very good one right there. Holly's Ferrotech General Catalog's helpful, Peach's book. And then you have the side books like McCabe and Smith. Perry's Handbook's not too bad. Crushing and Grinding there, and Powder's cool. Anyway, let's talk a little bit about machines for pressure or press agglomeration. Okay. This represents a large portion of size enlargement processes, quite different from other agglomeration methods. Different sets of technical issues and problems. Equipment orientation is dominant. You have the tabulating presses, you have piston, you have rollers, you have isostatic, you have extruders. Technology tends to be independent of particle size, tends to be. And this is probably a yes for most part, but no other ways. Forces are very high, right? Equipment is very versatile and complexity exists in the design. You have small and medium capacities. You're looking at 1 kilogram per hour to 50 kilogram per hour. Above the, 50 tons per hour. Above this, the equipment may have an option or a possible increased number of machines. Above 500 tons, equipment should not be used. That's 500 tons per hour. Dry solids are usually processed in relatively small amounts and oftentimes made in one agglomerate at a time. Not always, but made. Systems are easily cleaned and quickly emptied. Control is exact, and agglomeration occurs with or without binders. Anyway, the mechanism of compaction is shown here, and you have the near constant density. Since the air, you assume the interstices in here, which is most likely air, it doesn't weigh very much. At low pressure, the rearrangement of particles takes place, leading to closer packing. This stage, energy is dissipated mainly in overcoming particle friction. The magnitude of the effect depends upon the coefficient of interparticle friction. Be interesting to see if it gets hot enough to melt. Probably not. In cases of very fine powders, cohesive arches may collapse in material. The materials become de-aerated, less air. Now you continue on with pressure. This would be the intermediate pressure range over here. At higher pressures, elastic and plastic deformation of particles may occur, causing the particles to flow into void spaces and increase the area of interparticle contact. Interlocking of the particles may also occur. For materials of low thermal conductivity and low melting point, heat generated at points of contact may be sufficient to raise the local temperatures to a point where you have increased plasticity. Well, let's be honest, that melting facilitates particle deformation. So you have what was left up here, mechanism 1 is the input for mechanism 2, and particles deform, they may melt, they may actually, plastic may flow. So you're in the intermediate range where there's some slight densification may be going on. With brittle particles, the stress applied at interparticle contacts may cause the particles to fracture. Now you may have a fines production. I guess we're taking something like this. We're certainly not, we may be taking something like this. So the input here, or the input may be here. Okay. Interparticle contacts may cause particles to fracture followed by rearrangement of the fragments to reduce volume. As the process continues, the broken particles require increasing pressure to further fragment them due to increased resistance to smaller particles. So now we're entering where up here the black spaces was indicating a void. Here there's very little void spaces here at all. And we're in the high pressure range up here. And then the possibility we put so much pressure, when we release the pressure, there's a spring back. So we're at near constant density here. So this is log pressure versus log density. Machines that will do this sort of thing, well, we have a briquetter, which we'll talk about. We have roll compactors, which we'll talk about. Then we have tableting machines. This is how you make tablets. You can have a hydraulic piston going back and forth, pushing out stuff. Piston briquetter. Obviously, you may need a cutter device, cut it off. Eccentric piston again. So piston. You have your famous extruder. Generally, you should recognize the extruder does not mix very well. Okay, so twin screw extruder will mix, but a single screw won't. So if you're using it for a mixing device and you're getting poor mixing from it, well, that's understood. It's not a very good mixer. Then we have a 2-roll mill or 3-roll mill here. We have a pallet material. Obviously, the way it's shown is this outer die has to rotate. It has to rotate because the blades have to cut off. And these rollers are rolling the material into the die, and the die squeezes, the pressure on the roller squeezes the material through the die. And you have cutter device, and you get pellets. So we're looking at the binderless pressure agglomeration. Usually has high applied compaction forces. And one of the more of the following binder mechanisms may be occurring. You can be forming solid bridges. Cindering, remember we can cinder at temperatures 2/3 that of the melting temperature. Chemical reactions may be occurring, partial melting may be occurring, absorption, interlocking bonds, and of course our old friend electrostatics and magnetic forces. Some materials have natural binders or naturally containing binders. Other material must have the binders added. Agglomerates have freely movable liquid bridges. That's interesting, depending upon saturation, having substantial capillary pressures at the surface. Interesting, I was playing around trying to figure out how to talk about, capillary pressure. Give you an idea of capillary pressure, take a tissue and fill the sink up with water, put the tissue along the sidewall of the sink, and watch the liquid climb into the tissue. It's substantial capillary pressure happening right there. We have liquid in there, obviously under this set of circumstances. Well, let's go back here. Under some sets of circumstances, you don't want air to be around, or you may not want to have liquid being around. Because when you pressurize this stuff, you may be squeezing the liquid out. See, we're assuming air is sitting here, but if there's a gas sitting here. If there's a liquid in there, things change. Gases are compressible. Liquids are incompressible. You can have trapped air pockets in there, which is a major problem, by the way, because what will happen later on is they'll rupture the capsule or the pellet that it's in. So you got to start also, you're assuming gas here, which is fine, but it is a possibility that you have a wet material going on, wet material being. So if I take a look at the machines here, I got to worry about air maybe here. I definitely have to worry about air in here, or the gas I have to worry about. And I got to worry about the gas in here. Not so much here. Anyway, so you have the flow of the solids, right? Going back to this, the solids are flowing, but you have another phase in there, the secondary phase or the gas phase or the liquid phase, gas phase primarily. Got to worry about how that's going to get out. As you reduce and solidify, increase and densify, as you increase the material, you got to let the air out. If you don't, it will stay in there. Anyway, I want you to look through, go buy some cheap aspirin or some cheap vitamins or whatever. I have vitamin B12 I take, and the tablets are made very poorly. And every so often I have a tablet, a pellet, a pill. It's split open, and it's split open because of the trapped air in there. And the fundamental way of removing air, right, is run under a vacuum. It's not a hard problem to solve if you can run under a vacuum. So I can immediately envision that perhaps you got to have a vacuum with this hopper, perhaps. Hopefully, gravity feed without electrostatics is going to occur in here. And so you have some sort of free flow in here as this thing comes sweeping by. By the way, this is rotating. Punch direction travel. This thing's rotating, fills the, here the pill has been popped out. The lower press has been withdrawn, leaving a place in there. Hopefully you pulled in most of the gases, solids and little gas. And then you scrape off the top portion. And then you activate the top puncher, and the bottom puncher goes up a bit. You have a pressure roll to give you some pressure there. You have a pressure roll at the top to give you pressure there. So you put pressure on the capsule, and the top press face withdraws, and again, the tablet is pushed up by the lower press, and off it comes, pop. And the problem is in this compression, where is it? Right in here, going from here to there, you got to do it such that somehow the air gets out of there. Now, air chimneys might be. You can buy a funnel. Now, there's a funnel for, it's a device in the kitchen that you use to put it on top of a jug to use to funnel water into a jug of water, perhaps. Jug. You take a look at this funnel construction, and it's got ribs around the outer perimeter. Okay, outside the funnel, there's ribs. Now, you may think those ribs are there for reinforcement, but actually those ribs are there. So as you pour water or liquid down the funnel, the air can escape, or the gas inside the bottle can escape through the funnel as it sits in the hole of the jug with these ribs along the perimeter. Leaves a little air gap or air clearance in there. It lets the air out as you fill up the jug with water. So, you bought this funnel thinking, oh, geez, it's just a funnel. But after you notice the ribs and understand why the ribs are there, you realize that you no longer have just a funnel. You have a high-tech funnel, I'll tell you. Anyway, thought I'd talk to you a little bit about that there. Anyway, so we have all sorts of binding mechanisms or interlocking mechanisms, all sorts of agglomeration. Capillary pressure, again, the tissue in the sink routine. I'll give you an illustration of capillary pressure. It can be quite substantial. Agglomerates have low or medium strength. There you go. So you may have to age it, ripening it, or drying it, or firing it, or curing it. This is necessary because the agglomerate initially isn't very strong, and so you sort of cure it, and by curing it, you make it a lot stronger. Strength for sintering, chemical reaction, melting, saltification, all sorts of things can occur. Most versatile method for pressure agglomeration is compaction. Usually you're after pellets or briquettes, tablets or briquettes, where the size and shape are fixed. Okay. Under compaction pressures, particles approach each other. Strong bonds, possible fusion, grain boundaries, binders are not needed in most cases. Okay. Low pressure agglomerates is called pelleting, where the material with the binder is forced through dies and holes. Length, diameter is fixed for the dies, but the length may vary. They may be flanged open and flanged on the entry. Pellets usually require curing again to attain final strength. Compaction machines, low pressure compaction, particles are rearranged into a closer, denser packing. Energy is needed to overcome friction. Magnitude of interparticle friction can be high. It's an interesting question. That's how high if you have measured the temperature. Particles remain the same size and no deformation. Higher pressure agglomeration, you reach the elastic plastic deformation point. Elastic, it springs back. Plastic means it might flow. Interlocking particles may occur. Particles flow into void spaces and increase area of contact. Heat generated at contact may melt the material and or certainly increase the plasticity of the particle. Brittle fracture may occur. Brittle material may fracture to fragments which then rearrange. Materials with low thermal conductivity, that means the heat stays in the same place or has a longer residence time. A melting point may be reached, right? With low conductivity, a melting point, this causes the material to melt. Air entrapment may occur. And again, simplest way to take care of air entrapment is not have the air, and you run under vacuum conditions. It will make a lot of your problems disappear. Very high pressure agglomerates may cause an approach to true density of the material. There you go. Wow, that's pretty amazing when that happens. Elastic particles will flow. Elastic particles will flow. I should say elastic plastic particles will flow. Brittle particles will fracture. All mechanisms, densification occurs. All mechanisms bringing particles together, forces acting between particles become greater. Yield product that has higher strength than before. Higher strength leads to better handling. You have no breakage occurring when you handle this stuff, or breakage is reduced. Compaction reaches the bulk compression. Broken into foreign particles can no longer change position, relatively few remaining voids. Interparticle conformity occurs. Apparent density approaches theoretical density. Theoretical density is material without any voids, right? Rate of compaction depends upon the yield point of the material. Oh, yes, yield point. That's when it starts to flow. Brittle material is more difficult to compact because it doesn't flow. Fragments decrease with time. Fragmentation decreases with time. Voids may be disconnected and pressurized. That's what you don't want right there. Pressurized. Compaction energy is stored as elastic compression. This is what's going to cause your spring back. Disintegration of compacts occur upon the release of pressure, the release of stored elastic energy. pressurized, avoid depressurized. You got to let the air out. Material doesn't compact uniformly due to internal energy effects, due to end effects and frictional effects. All right. Variations in local density occurs upon compaction. This leads to a weakening of the compact. Somewhere there'll be a lower density or a variation. Higher densities occur nearest the compacting surface. So you have some sort of surface hardening effect going on. Lower densities are further away. Density variations increase with increasing applied pressure. That makes sense, right? Increase in the size of the compact. That makes sense. Decrease with increasing diameter. There you go. Round is easier to make than square. And if you're looking for density variations, then you certainly would compare the corners of the square with the center of the square. Density variations are reduced by lubrication of the die walls and the pressing tools. Also, again, you're looking for ways of getting the air out. Segregation during feeding and filling leads to density variations. Yeah. You have a mixture of solids. Maybe you have small particle size, large particle size. Maybe you have electrostatics. Maybe you have dry, no electrostatics. So they don't all, the particles do not flow or behave the same. You have local changes in particle size distribution. The bigger particles move on, the smaller particles may be adhering to the wall. So if I have, this is stress contour levels in a square centimeter, density contours, right, and this is a reaction force. We're primarily interested in A and B. If you look at the corners, what do we got here? We have, this is the pressures applied at the top here. So the far corner is going to be less dense, right? That's dense. Apparently, high pressure is spread out to the wall, resulting perhaps in lower pressure right below the contact point. That seems a bit unbelievable, but possible. Okay, these are, what did we say? The stress contours. Lower density, lower stress. So these overlap essentially with these, right? So stress density patterns, right? So the idea of segregation during feeding is really can easily occur, can easily not be recognized. What's really funny is, you know, just what I understand of all kinds of things, I'm a little scared about whether my pills that I take for my various ailments are been uniformly mixed. Anyway. And whether during the filling operation, the active ingredient didn't somehow make it into a few pills. Anyway, let's go back and catch that sentence again. Segregation during feeding and filling leads to density variations, causes differences in plasticity and friability. No large flows of powder occur during compaction. Variation of density before compaction can have an appreciable effect on the variation of density after compaction. Well, yeah, that's pretty much a given. Right? Fill it wrong, be wrong. If you fill it wrong, that means the container has wrong fill, and when you make the compact, it will also show up in the final product. The relationship between compacting pressure and density is important. Do you know what that relationship is for your particular machine? Empirical equations are available to describe pressure versus porosity. Now, porosity is extremely important. Well, it measures the amount of air you got in. There is no such thing as a porosity meter. So what you might do is take one of your tablets, one of your pellets or whatever, your agglomerate, and sand it down or remove different layers, photograph it, remove another layer, photograph it, remove another layer, photograph it, and then play the photographs of all 70 or 8 photographs you've taken as a continuous video. And perhaps you can understand the distribution of pores or air pockets in your agglomerated material. Equations are useful over a limited range, material-specific, different to quantify. Well, the idea is first you got to get the information before you got to get the data. And again, sectioning, taking pictures, section, take another picture. Pressure controls the attainment of high density, strength, attainment of low porosity and poor porosity properties, desired final product qualities. By the way, porosity is very useful in capillary pressure and dissolving. If you're trying to make a pellet that dissolves easily, well, you may want to have a very porous material or a very porous. You want the particles to fuse together but have open spaces between them. Die pressing, the oldest type of agglomeration technique. Die pressing reminds me of in making wine, you have these villagers stomping grapes into a big vat. And I'm thinking that that's sort of like think how long that's been taking place. Die pressing used in a variety of industries for a variety of purposes. Largest users, pharmaceuticals, used in ceramic, powder metals, foods, candies. Divided into 2 categories, reciprocating single-stroke machines and rotary machines. Anyway, let's take a look at what we got here. So we have the industry and we have the example of product. I mean, look at fish pellets or dog feed or, right, foods, vitamins, tablets, nuclear, element pellets, ceramics, disposable cutting tools. Okay. Usually reciprocating machines usually operate with one upper and one lower pump or piston on a single die. See what happens with our tabulating machine. Let's take a look at our tabulating machine. This is a rotating table right here, right? So these are fixed. So you have something that is moving the table on by, and these things slide up and down. These don't have to rotate, right? You want the pellets to be able to be ejected at one particular location. Anyway, let's see where we were. Okay. What else do we have here? Let's see, used for complex shapes and high pressures, relatively low output, 100 compressions a minute. Well, that's not our tabulating machine, basically. Ejection presses and withdrawal presses. Ejection machines vary from simple hand-operated units to highly complex machines. Pressures may be up to 1,000. That M is supposed to be million newtons per square meter. Produces highly precision and accurate compacts. Die is a fixed plate with upper or lower punches attached to a moving ram. Lower punch allows the die to fill. The upper punch compresses, gets the stationary lower punch, and the lower punch ejects the compound upward. Have a full range of mechanical and hydraulic presses that have been developed. Small machines with limited output for developmental work. Larger machines for powder metals and ceramics. So what do we have here? Disadvantages, right? Produces compacts with very considerably in density from top to bottom. Pressure exerted by the top press only. Tablets which disintegrate more rapidly on one side. Produces tablets which disintegrate more rapidly on one side. This is a big problem for ceramic and powder metal parts. Different densities have uneven shrinkage rates during sintering. Right. Here's a picture of something what we're talking about. We have a die here. We have a bottom punch, and we have an upper punch, and we have basically a core. And your fill area is the annulus. So you come along and the core is going to size the inner diameter. The punch and the core have to match here. The upper punch has to match the core as well. Here's the sequence. You have the fill. So after you have the fill, you have the punches hit. The lower punch continues to push on out and withdrawal. The other one comes in at the top. I mean, this is pushed off to the side, and there's the next filling operation to undergo. Right. We get the picture here. Start as die is positioned above the lower punch filled, the upper punch descends, presses the material. In the die moves downward, maintains uniform density, upper punch retracts, the die continues to move downward, or upward, I guess. Die continues to move upward, ejecting the compact. Got a little typo there. Lower punch doesn't move. Upper punch retracts, die continues to move. Says the lower punch doesn't move. Well, the lower punch does move. If I take a look, this is the lower punch. Well, the lower punch, it has to move back. It has to do this. All right. Anyway, looks like all the punches are moving except up here, the two punches are not moving, the top two punches. So you have movement in the top punch here and here. Here it's stationary. If that's what they're talking about. If that's what we're talking about, I should say. See what we got here. Complex, expensive, requires complete movable die set and replacements, of course. Adaptable to complex components. High accuracy, dimensional tolerance is less than 4 times 10 to the 4th minus 4 millimeters. It's pretty small. And here we have operating schematic for a rotary tableting machine. Right. Things to watch out for. Again, my paranoia about whether there's been medicine left on the hopper chute here. You got a problem with getting the air out, so lower punch might have some porosity in there to help get the air out. Keep the solids in and the air out. Uneven density effects are not very pronounced in rotary machines. Punches are moved by a series of cams. I think we've already pretty much just discussed how the operation is done. Excess is scraped off, retracts applied. Anyway, you can understand it better visually than reading it here. No liquid type of powder flow occurs. No flow due to pressure gradients, no flow due to hydrodynamics. Simplest machines is one-sided, 1 feet location. And we're looking at 1 tablet per revolution. That's pretty low. Well, you'd have 1, 2, 3. 3 would be kind of interesting. Output, you're looking at 300, 800 tablets. If you double-sided 2 feed positions, 3,000 tablets per minute. These are what are called acceleration machines. You start and stop, right? The dies are started and they're stopped. So they're accelerated, and it's only so fast you can go. With acceleration machines, you reach the tolerance and you can't accelerate any further. Further capacity improvements can be attained using multiple side-by-side dies, and that's interesting. Think of it as you have a huge belt. It's a very wide belt. And across that belt, you have 20 or 30 cookies. And you have row after row or row after row of cookies. And each one of those cookies is being initially formed by a jet, some sort of jet stream. So it'd be interesting if you could do a cookie belt effect in making tablets. I mean, if you take a serious look at a cookie, it's just nothing but a poorly formed tablet, right? Anyway, there's no pressure been put on a cookie. I mean, there's no dies coming down, smash it around. And so it'd be interesting if you can get away from this approach of doing 1 tablet at a time, but you do a row of tablets at a time. Hey, now we're cooking with gas, huh? What do you think? I wouldn't be a bit surprised if that machine's not already available. Since I thought of it just now, it's not that hard. Think of that. I'm no profound great inventor here. I would imagine that machine's being produced somewhere. These mechanical engineers are absolutely sensational from what I can gather. I, being a chemical engineer myself, somewhat mechanically inclined. Anyway, somewhat mechanically inclined. Now then, what tablets can be made? Well, single punch, rotary punch, and this is 1967. They're about it. Now, this is 2020, so this is old stuff. Huh? What do you think? Anyway, I'll leave you to find out if there's tabulating belts. It would be a tabulating belt press. Anyway, the tablets that can be made are these shown here. And again, your assignment is I want you to go through your medicine. If you buy a cheap bottle of aspirin, you'll find that a number of the aspirin tablets may have already broken apart. You also will notice that shallow is good. Shallow is good. No abrupt corners. No abrupt corners are good. Notice how they're rounded. No spheres. I've been told that spheres are not possible to stabilize. So oftentimes you have mixed, what we call mixed segments, right? Right. You have the top cap, lower cap, and the middle. You might make each one of those separately and then fuse them together. You have 1 chemical in here, or 1 medicine in there, 1 medicine in the middle, and 1 medicine at the top. Kind of interesting. Then you can put your little brand name on there. That'd be kind of cool. In fact, you could say, you could have things on there that give partial directions, like not for children, or don't feed dog, or not for pets, you know. And then you can make them striped with color. There's a lot of, I'm sure that they're out there. Anyway, I just haven't caught up with them. Design features and variations. Well, die and punch shapes are varied and may include facets and compound caps. Well, special tapes are available. Fat, thin, pear, oblong, center hole. Yeah, I doubt if lifesavers are made with a punch, but you know, tubular, square with rounded corners. Yeah, you better have rounded corners. There's nothing more asking for it in the world of tablets than a corner. A corner is just simply sitting there asking for it. Complicated shapes are produced but need proper feeding. Punch and die members having a correct shape, proper supported release shape. Different shapes are usually made with mechanically operated die. The die hole itself you got to pay attention to the die hole itself, right? Because eventually it will get washed out, right? And how it washes out and wears and how much life cycle do you have? Dies consist of eccentric, crank, toggle, ram, anyway. Design variations increase capacity, multiple dies, multiple tips, 2 filling stations, first layer, feed, second layer. Automatic powder feeders are needed. High accuracy of volume and density. You know, what strikes me is that scraper back up there on that tabling machine. But look at that, they have this scraper here. Now, I'm really worried about how effective that scraper is. Wonder what happens with that excess. Right. I want to know the retention time of any retention time that's made upon that surface. Anyway, we already talked about this. We further on. Complicated shapes can be produced, but we already talked about that. Let's see what else we got. 2 filling stations, high accuracy. Feed needs to be free-flowing. Aha, there you go. Automatic feeders are needed and used. High accuracy of volume and density. Okay, good. The feed needs to be free-flowing. If it's not free-flowing, then perhaps pre-agglomerated. Ooh. If it's not free-flowing, that means there's a binder of some sort inside there, and different causes problems in feeding. Different feeder types include, there's some different types, actual designs vary, direct shuttle, metered shuttle, arch-type shuttle. Right, we'll let you find those out. Well, let's go back. Straight line, reciprocating action. Connected directly to supply hopper action is inline or linear. The same except a metered amount of material moves to die. Arch type is pivoting or a rotational action to move the die. So there are some advantages. Feeders should be such as to prevent air from filling a cavity. Insufficient de-aeration and compressed air pockets can cause tablet failure. Okay, so this is the idea of getting the air out. Die pressing is most versatile agglomeration methods, a variety of applications, complexity of shapes, accuracy of parts, great variations in manufacturing, and well-defined parts. I guess corners are accepted by this statement here. Okay, strikes me as corners will be difficult. Or you have rounded surfaces which cause no problems, and then you have cornered surfaces, whereas you can produce them. They will always wind up being more difficult to produce than curved surfaces. So maybe one of your design features should be to eliminate corners. Everything having a rounded Other types offer one shape. Accuracy of different sizes very limited. Accuracy on different sizes very limited. Well, tumbling agglomeration, for example, offers only one shape. But if I'm trying to make one shape, say in a pan pelletizer, I will have variations in size on the pan pelletizer, and that's probably the best with tumble agglomeration. Still, other techniques offer a relatively small number of shapes with some accuracy. Roll presses and tabulating machine. If you take a look at the aspirin coming out of a bottle, they're all the same. It's amazing. Disadvantage of die pressing is the tonnage is quite limited. Disadvantage of all mechanical drives is the brief time of maximum compression. Basically, it'd be interesting to see if you can, at maximum compression, if you could hold that for a bit. Right. Some material have elastic properties which cause you to have spring back. Right. There's a need to remain under pressure for some time to reach maximum deformation, to reach permanent deformation and strength. This is brief time. Here you want one that has long time or at maximum compression, longer time at maximum compression. So what design will give you that? Premature pressure release results in excessive spring back, which may affect structural integrity of the compact. Overcome the problem by hydraulic presses, hydraulic punches. Dwell time can be adjusted, overload protection can be incorporated. Hydraulic punches have an additional advantages, allow densification of large amounts of feed. There should be no S there. No physical limitations on stroke length. Wow. Pressure rise can be slow, final pressure can be very high. However, long dwell times can limit capacity, obviously. Failure modes and quality issues. Laminations, basically layer separation. You may not think that you have lamination in there, but you do. And if sort of like snow has different, if you have different snowfalls, each layer of snow is different. Capping is separation of a thin layer of tablet from the main body during and after unloading. Caused by excessive elastic recovery or spring back or decompression of trapped air or trapped gas. Unfavorable geometries. The idea of trapped gas pushes the idea that you shouldn't have gas around to begin with. The real kicker is you run in a vacuum situation. Right. Favorable geometry should be shallow, well-rounded, not narrow. There you go, not narrow. Limited capability of what can be produced. This shallow, well-rounded, narrow. Need to maximize limit, not too narrow. That's too TOO. Need to maximize density gradients. Excessive density gradients cause the destruction of the compact. Let's go on over here. Anyway, capping, laminating, cracking, and other problems occur because of density gradients, or they may occur along density gradients, normal to the gradient maybe. Other problems occur during finishing. The use of lubricants is often used in die pressing to keep friction down and help the release. Lubricants are an impurity. Need to keep the amount down as low as possible. Excess lubricant layer can cause failure. If blended into the mix, can reduce product quality. Need binders to act as the lubricants. If you're going to have a binder in there, right? We didn't mention, it might have been mentioned, I didn't catch it. Non-free flowing feeds have binders in them already. If the feed is non-free flowing, you have binders in them, and it causes a feed problem. You may not be able to distribute your feet. See what happens if we go back to my tabulating machine again. I'm sorry. Okay, this is implying a free-flowing powder. And it may not be a free-flowing powder here. So you may have a distributor, you may have pay more attention to this situation. This is for free-flowing solid powders, this ain't no problem. But when it's not free-flowing, then you have a problem. Two types of powders in the world, free-flowing and non-free-flowing. Okay. Where were we? How we were talking about the feeders, insufficient deaeration, advantages, disadvantages, spring back, long dwell times. Where were we actually? Should keep track of this. Lamination and capping going on, favorable geometries. We're talking about lubricants. Binders are present in non-free-flowing powders. That means they're going to be difficult to feed, so you may need distribution. Operation may need to coat dye walls and tooling with lubricants. Or, you know, in a sense, it's called releasing agents. And if you were doing foundry work, it would be called release agents of sorts. Nozzles and electrostatically charged lubricants are useful. Electrostatically charged lubricants, that's kind of interesting. Electrostatics tend to go wherever the metal is. So here's a list of lubricants. I don't know which one would be electrostatically. Water, being the most common binder, also a very common lubricant, shorts out static charges. Disadvantage is the application takes time and must be incorporated in the cycle. The dye cavity can be filled with air during a lubricant application. That may not be desirable. Other problems occur which can be overcome by using processing options. The way you, like I said, the way you solve, or I have said in the past, the way you solve the difficult problems is that you don't. You don't solve the difficult problems because probably they may not have solutions or a good solution. So the best way to solve a difficult problem is go around the problem. So special coating, vacuum operations, think about cooling down or heating up, cooling your dyes, heating your dyes. So, you know, you have various options here. Alrighty, so tolerances and finishes of dyes are very important. Design, manufacture, mounting of non-cylindrical dyes are possible. Requires special experience and skills needed to produce the dyes from abrasive-resistant materials, have high tolerance, high quality finish. Walls are slightly tapered, of course. And some punches serve as dyes, have to be manufactured as dyes. Anyway, more on equipment, talking about roll presses. I'm going to take a quick break. Whether you notice it or not, I'm not sure. Okay, let's talk more on equipment for pressure agglomeration. Okay, talk a little bit about roll presses. Okay. Well, applies to a wide range of materials, has the capability of compacting large quantities of material at low cost. Other features possible, easily implemented. General comments, much is not known, present knowledge is still phenomenological. Comprehensive theory of densification of particulate matter is not available. So let's see what we got here. We have different materials sitting here. We have the roller diameter used, the maximum roll face width in inches, 3-6 inches. Roll separating force, 25 tons, woohoo, 150 tons, 300. B-plex, again, this was probably taken don't know where it's from, but I'm sure you can update it. The important design variables are here: diameter, roll face width, and roll pressure, or roll force, sorry. And these are material properties. There's a lot of information, performance data. This contains a lot of performance data, right? Many similarities exist between deformation of metals during rolling. Roll pressing is still an art. Falls into a fairly undeveloped area, plastomechanics, basically. That's the mechanics between a flowing fluid and solid mechanics. So it's in between there. We're going to assume that makes things easier. The material is homogeneous and uniform in all directions, or isentropic. So it's homogeneous and doesn't have any directional preferences. Elastic deformations are relatively small compared to plastic deformations. Elasticity is secondary to plastic deformations. We are looking for the ductility. What is the ductility of it? Do you know what the ductility of your material is, and how are you going to measure it? So you have a device that perhaps you can measure Hooke's constant, or you can measure the stiffness of a material, right? And maybe you can measure the yield point, and maybe you can measure the ultimate stress on materials. But the ductility and how you actually use it and what the units are, and what sort of strain rate do you have to measure this ductility? I myself am not educated in this area, so I'm going to be quiet. But it strikes me that you should try to attempt to figure out how to measure that, put a number on it, put your units on it, and I'm sure it varies. I'm sure this term varies with all sorts of different types of materials. Materials can be stressed to cause the flow. Yep. Reaches a yield point, some material will break, different curves. So you need to determine the type of material and behavior you have. Rock, metal, plastics, paste, powders, they all break and have ductility in different ways, I'm quite sure. Breaks, flows, melts, flows again. Excuse me, melts and flows. So breaks, flows, I would say melts is the next step. Melts and flows, kind of all kinds of things that can be happening in there. Sort of like reality meets reality check. Basically, double roll presses, squeezes the material between two counter rotating rollers, indentations in working surfaces, form shapes, forms, briquettes, and compacts. So we're looking at something like, let's jump ahead for a second. Let's go to this one here. So you have one roller. You have some pressure build here, very high pressure in what is called nip. You have a product, lots of airflow that's going on. We'll talk about the airflow in here. I suspect some of the air passes through, some of the air gets circulated back out, and the air coming back out might interfere with how the feed is distributed in this nip area. So we'll come back to this slide a little later. So that's occurring right here in this slide. You have force feeder. That's what indicates that this is. You actually have the distance between the rollers. So this may be compressed, high compression rollers. This could be a high pressure compressed, what is it? HP roll crusher, HPRC. This is typically a roll crusher in the crushing industry. Now we're turning it around, and instead of crushing, we are agglomerating in the agglomeration industry. So very interesting. Same machine used in two different places. So here the hydraulic actuator, pressures exerted on the rollers. If in case you have something that It's non-free flow, excuse me, that's large, that's solid and large, that's coming through, that's not necessarily a powder that you were anticipating. So then we have a pre-breakup into sheets into chips, and then down here we have a granulator. Now this granulator has size. Screens are important because that determines the size of the material exiting. Then you throw in a screening operation to remove your oversized products to be recycled and fine products, fine stuff to be recycled. And you have the original feed, powder feed here, and they're mixed in a recycle system. This apparently is feed and recycle. And you again recycle when you have stuff that feed comes off in the middle screen, comes back down. You should learn about screening operations, right? Screening may be important to you. Anyway, I would oversized material. Hopefully there won't be that much because you have a screen here prevents oversized material from getting through. But you may put in a kicker mill. Kicker mill may not affect your fines, certainly, but it will affect your, if there is any oversized. Rollers are timed and matched to form shapes. Shapes do not have fine detail or uniformity as a die press, right? Detail and uniformity is not needed for, say, fertilizer pellets. Feed is an important issue. Gravity feed at the nip, no pressure mechanism. Screw feeders provide positive pressure, force feed. Feed can be controlled. Nip area is divided into a feed zone and compaction zone. So what we have here is a feed zone up here and a compaction zone down here. Material is pulled into the nip by friction. Intensification occurs due to particle rearrangement. Bulk density goes to the tap density. So, give you an idea of what I'm talking about. I got an experiment I want you to do. You get a ground coffee in a coffee can, right? Metal coffee can. And go down about half the level, so there's a 50% coffee and 50% air in the can. Okay, and I want you to note the coffee level in the can. And then I want you to take the can and tumble it. 1, 2, 3, end over end, making the coffee go back and forth. And what I want you to do is take the lid off the coffee can and look how much coffee you've created. The level will be higher. Most often will be higher. If it happens to be very dry where you're at, it will be a lot higher. Anyway, the particles create a static charge with each other and repulse each other. So that's why there's a volume expansion. And moist air will short all that out. So you could have half a can of coffee when you go home at night and dry air by the next morning where moisture's coming in. That shorted out the static charge, the coffee level will drop. So you have coffee, lots of coffee when you go home, and shorted out coffee when you come back in. Have you noticed that? Huh? I haven't, but I'm anticipating that I would. Maybe I'll have to check. Anyway, so you have a lot of interesting things about. First off, you have feed here. Okay, you have motion, you have material. So you have a static potential of a static buildup. You haven't had any sparks come off that feed pipe to the rollers, have you? So I can envision roll crushing where there's static charge buildup. Anyway, I always want to watch out for static charge myself. Where are we? Here we go. Full densification occurs. Tap density. Tap density is as close you can get by tapping, I guess. The particles get as close as they can be. tapping. Of course, then again, with static charge, that tap density can be quite meaningless. One day you have a tap density of, say, 1.2, and the next day you have a tap density of 0.9, just because you got to worry about bulk density. So I'm really concerned about exactly how the tap density is determined and what value you have for it. Perimeter speed of the rollers are higher than material velocity, okay? Compaction zone follows, pressing forces become effective, particles plastically deform, density reach maximum values, material reaches the roller speeds, the extruder zone may follow contraction, material accelerates, releases. So here's the picture of it here. The idea of it there. So what I really want to know is this here. Let's take now, reevaluate what we saw here. We have two rollers like that, and we have our feed coming in. The feed contains air. Now then the solids are pulled into the zone, or pulled in together, and pulling the airstream. Now the airstream may actually reverse direction and flow upward. Solids will continue downward. The airstream may actually start to fluidize the center portion of the powder in here, right, leaving potentially a void space. So you have partial fluidization of the solids, preventing the solids to be fed appropriately. And see, this is pulled inward again. So you're leaving zones in there where the solids are no longer at the tap density. They are actually sparse regions of solids due to the fluidization that can be occurring in this solids fluidization that can be occurring. The airflow rate in here is shown by this velocity profile. You have flow down at the rollers and up in the center line. And that situation, if it goes on through, will leave you regions of sparse solids and high concentration of solids. The exit for the air is actually blocked here because of the solids being densified. So what will happen is you'll have material coming out, agglomerated material coming out. Then you'll have powder feed, unagglomerated, then more agglomerated material, and then powder. So it will be intermittent operations in the densification. Now in our loop, remember what happens to fines? We go back to our loop here. So we have the compaction, and if it's operating where the fines get passed on through, the fines get passed on through, goes through here and comes out all the way and gets recycled back up. Right? So fines are not necessarily your friends. Or the fluidized particles, which would tend to be fines. There could be a separation process in there as well, where the finer particles are fluidized upward and the larger particles are pulled downward for intermittent operation. Yeah. Anyway, that gets fun and games here. Go back up here. We also got to worry about particle size and fines. Right, we were here. We got to worry about this graph here. You have air pressure in the material, very high air pressure, very impermeable solids. So the solids doesn't let the gas leave. You have coarse and very permeable solids, lets the gas leave. Intermediates. See, the fines are what's going to trap the gas in here. Fines are going to be such that it's not going, it allows the pressure, air pressure to build in the material. Whereas here, if it's permeable, there's no air pressure. So now we have to worry about the porosity of this material in here, how porous it is. Porosity being a function of particle size, and particle size determines the porosity. Anyway, it may look simple, but from the point of view of particle physics, particle size, electrical charge, agglomeration, surface effects, fluid mechanics, powder flow, it can be quite complicated. Briquetting process, fortunately, is different. Rollers have pockets. There's no clearly defined feed and compaction zone. Before plastic flow begins, you have plastic deformation derived by Hooke's law, so you worry about brittleness. Flow conditions can be determined from stress. Analytical solutions can be attained in only a few cases. So we have a number of angles in here that we have to worry about. Zone feed angle, feed bulk density upon entry, tap density. So we got right in here. So we have the original feed, and then we have what we're interested in is HA. That's what's going to come out. And then it's elastic release, which is HS. So we have a number of different angles. Lots of mechanical engineers and people have spent a lot of time talking about what happens in the nip, right? Well, all the different angles involved. Let's see what else we got. Delivery angle. Terms for compaction zone, angle of the rolling, that's alpha E. Neutral angle, alpha G, where force direction changes. You have elastic compression angle, determines HS. There's no recycle, alpha V is 0, and HS equals AA, excuse me, HS equals HA. Lot going on in the feed zone. And if your feed is not the same, and it's variable feed, varying particle sizes because it came out of a bin and the bin was stratified, holy tamale. Lots of problems, yeah. Let's move on. We also have the gripping angle. Size of the feed and compaction depends upon the roller diameter. Volumetric output is the gap width and the velocity. So we have the gap width times the velocity. Velocity is ND, excuse me, pi ND. Output velocities H, or excuse me, output will be H times the area A, and then times the speed. A is what? I got to figure out what that A is. Well, this has got to be length. This H, I figure out what that H is. If I go back here, here is H. And A is probably the length. So it's the H is the width of this, right? So it's HA, and it might have to be a subscript. This could be possibly H subscript A pi ND squared. That would be height times. It would be area flow, area per second. Or it could be, well, volume. Excuse me, this has got to be area. Okay, area times velocity is volumetric flow rate, right? Got it. Large diameter rollers, N is reduced. Got to figure out what N is. Rotational speed, slower. Gripping zone is larger for larger diameter rolls. Compaction is more gradual for larger rolls. There's less elastic spring back, less entrapped air, improved quality on with larger rolls. On scale-out processes may improve. Whatever small scale process you are running, large scale, since you have these things happening to you, then your large scale may be very important. Formulation to relate roller diameter, gap, HA, and porosity. You have porosity, tap density, compaction, the compaction strip angle. This equation is nothing but a mass balance. I would love to prove that to you, but the facilities are certainly not available, nor is the time. Anyway, it's a mass balance. Porosity, and you have a function of HA, which is controllable alpha diameter. Roll diameter is for relatively little densification. So we have compaction being C. C, we got this definition as well. That's probably a mass balance as well. A couple of mass balances floating around. High densification usually means larger diameter rollers. Larger rollers are more expensive. That's a problem. Force feeding systems can be used to reduce roller diameter. That's possible. Density control can be attained from force feeding. It's possible. Roll gap. First thing you want to recognize is rough approximation is HS equals HA, right? If you go back and figure out what HA is and HS, they're very much down here. And there's very little elastic spring back. Okay. That's the first approximation. Strip density or final density, you have the tap density, you have HA, you have the alpha E. So the diameter of the roller. And voila. Easy way of scaling up, go back to scale up here. As you increase roller length. Hopefully, as you increase roller length, the process is the same as you go down the length of the roller. Okay. So the longer the roller length, the more production you can get, up to a point to where the roller starts to flex on you and flexes a little bit or a lot. So that may indicate that you have to buy 2 or 3 rollers, not just 1 roller. Scale up is by increasing size of the equipment, that's true, or by increasing the number of equipment. Scale up is done by number. Scale up is done by design or simply repeating what you already have. Usually HS is slightly larger due to elastic recovery and trapped compressed air. Expansion under pressure release is influenced by the characteristics of the material. That means you got to experiment. Expansion is also depends upon roller diameter, surface configuration, speed. Better deaeration during densification occurs, larger rollers and slower speeds. Mechanical deformation occurs during rolling and include elasticity of the machine frame. That's pretty funny. The rollers can deform as well as the support frame for the machine. Things are not easy here. Okay, deflection of rollers and shafts. Elastic deformation of the roller surface and clearances and bearings. Wow, that's gotten deep real quick, didn't it? Gap set under load conditions is usually different from the gap set under no load conditions, usually different from the gap set under load conditions, right? Whether you're running or not running, gap will change. They depend upon the material. Compressing something is which is usually incompressible, right? Dynamic roll gap needs to be considered. What they're talking about is the fact that if you're not rolling, right? If you're not rolling, you're here. You have one gap, and when you're rolling, you have another gap. This distance is dependent upon whether you're working or not working. It can be quite different. That's interesting. Okay, roll speed. Well, it's assumed the peripheral speed of the rollers and the speed of the material are identical. That's not true. This is not true. Throughput does not increase with roller speed, so your starved conditions may occur in the impaction zone. Too much slip occurs between roller and material, Air sneezes from the material upward and partially fluidizes the feed. Starved conditions leads to problems. That's what I was talking about earlier. I guess you can, this has been called sneezing. Is that what we call this? Right, sneeze, it's squeezed. Air is squeezed, but in a sense, this is sneezing. Put a human aspect to it. Anyway, it's squeezed. Right. Starved conditions lead to problems. Not enough compaction formed for stable, compact, intermittent operations can cause severe chattering, vibration, and equipment failure. Rough or corrugated pocketed rollers reduce slippage between roller and material. Increasing roller speeds, more elastic deformation occurs and remains in compact. Problems in the product may arise, right? If you deformed an elastic material and the elasticity hasn't been relaxed, elastic behavior hasn't been relaxed, then it sits there and it's just like a time bomb waiting to go pop and release its elasticity. That's what that means. Problems in product may arise. Breakage, curling upon release, partial splitting on release. Anyway, I don't know if you've experienced this before. Again, the problem phase, whenever I deal with a process, I worry about what the problem phase is, and the problem phase is air. Best way of handling air is not to have it, oftentimes. Okay. Operations under starved conditions leads to holes in sheets, soft strips, and uncompacted material. To avoid starved conditions, material must fill the gap faster or as fast as compacted material moves away. There are, again, we're force feeding, right? Rate at which compacts move away is determined by roller speed. Feed rate can be estimated by pouring feed material into the set of stationary roller and increase the feed. Low mass flow rates, material passes through, no hold up. Low flow rates, there may not be a compact, no influence of roller speeds. At a higher speed to match feed rate, the material passes through and forms a compact. At still higher feeds and the roller capacity material builds up, which means the buildup of materials means that the speed can be increased. Increasing feed rates and roller speeds until problems arise. So it gives you the conclusion that a wide range of roller speeds are possible. Problems of speed can be minimized by having a gap selection capability, adjusting the hydraulic pressure. Overfeeding results in backup and spillages. Underfeeding causes large amounts of recycle and quality problems in compacts. Right. Roll feeding, simplest form is by gravity. Might call this choked feeding. For hoppers, discharge rate and bottom pressure increases with the height of material in the hopper, right? Up to a certain point. The hopper may actually bridge on you, who knows? A certain height, discharge rate, and bottom pressure remains constant. The solids inside the silo are supporting themselves. Point at which the material, that point varies with material, is typically occurs at 1 to 5 times the hopper diameter. Feed pressure is an important variable for operation. Should be as high as pressure as possible. Compact strength and density improve with increasing feed pressure. And in feeding, 2 effects are produced which tend to counter each other. And let's see what those 2 effects are. Air squeezed from the powder escapes up through the center of the bed, fluidizes the feed. Center of the compact fluidizes the bed. Particle flow is slower near the walls, which produces a starved condition at the edges of the roller. Need to separate feeder behavior from rollers or have a force feed system. Given all the variables in feeding system, roller design, surface, particle characteristics, Experimentation is necessary. In other words, you can do your computer modeling, but it's more important to figure out what's happening, especially when you have your material variations. To make full use of transport capability of the roller, need to have angle of delivery greater than the gripping angle. Feeder width should equal roller diameter. Many applications, compaction needed is small. Commercial rollers and pockets provide too much densification if choke feeding is used. Material flows to the nip is deliberately restricted to avoid over-compaction. In other situations, some materials cannot achieve the desired compaction in a single pass under choke conditions. Several passes are needed. Pre-compaction. Pressurized feed should be used. Pre-compaction. Oh, yeah, here we go. Pre-compaction. May also be considered, can reduce roller diameter by 50%. You look gravity feed pressure, screw feed pressures, so they're 100 times greater. Reducing diameter can cause an increase in speed to maintain production. Increased speed reduces compaction time. May become the limiting factor. Process optimization exists. 3 effects for optimization: roller speed, roller diameter, and pre-compaction. Right. Air entrainment effects are handled by rotational speed. Particle characteristics are unknown with regard to speed, diameter, and pre-compaction. There is a minimum compaction time. Upper limit for rotational speed, 2 meters a second. Complexity requires batch tests to obtain trends. Pre-compression force, roller force needed may be 25 to 50% reductions. Reduce roller size and roller force by pre-compaction. Lower sizes, weight, and cost of the rollers. Drive requirements vary with production rate. Pre-compaction is possible. Pre-compaction is possible by feeder screws. 1 to 100 psi, 400 is possible. Permeability of the densifying bulk mass must be high enough to allow the train gas to escape. There you go. Permeability of the densifying bulk mass got to be high enough to let the gas escape. Screw feed pre-compaction will take 20% total power input. Right. Optimum pre-compaction feed designs may vary, depends upon quality desired, depends upon shape, depends upon material properties. Many variables needed to be tested, investigated. Different feeder designs, right there. Different pre-compaction levels and different effects of recycle. Recycle has its pluses and its minuses. Recycle will have to be crushed and ground again, right? It's likely to contain a binder or a lubricant. Recycled broken compacts can lead to a new product. There you go. Scaling methods tend to be unreliable at this time. Special characteristics of roll presses. Well, controlled and complete removal of excess gas is important. Correct and sufficient venting becomes most critical when handling large bulk volumes. Densification of 2 to 1. You have 2 going to 1. That means about 0.5 cubic meters of air per ton of material. Or if you're moving 80 to 100 tons an hour, you must vent 40 or 50 cubic meters of air per hour. The thing has a lot of air moving around in it. Smooth cylindrical rollers have to be used in many applications. Grip angle becomes small, reduces compaction ratio and throughout. Force feeders help solve problems, particularly for small diameter rollers with fine particles. Rough surfaces increase the grip angle. De-aeration occurs more easily. However, rough surfaces, this is on the rollers, of course, rough surfaces wear away with time and only limited value. I mean, how long has your roll crusher, or excuse me, your roll compactor been operating? When's the last time you changed out the rollers? Smooth roller machines are needed for high throughput and abrasive solids. Advantage: smooth rollers, rugged design, easy manufacture, easy refacing, lower cost. 3 different modes occur: large diameter, smooth roller presses. Mode 1, homogeneous sheet across the whole length. Mode 2, sheet varies across the length with varying density and porosity strips. 3, extremely dense strips with air and loose solids. So mode 1 occurs most easily with small roller diameters, narrow gap, low speed, low capacity, and little entrapped air. Makes sense. Less air, less problems. Trapped air can lead to explosive relief and serious destruction and bursting of the compact. Popping sounds are heard. Sheets break into silvers and irregular shaped pieces. Here's a place, we already talked about that. Disintegration due to power can occur. Damage depends upon the strength of the compact. Always some reduction in quality. Desirable to remove gas most of the time. Problems created removing entrained gas. The gas flows countercurrent to feed in the nip and hinders free flow of solids above the nip. For fine feeds with low permeability, no compacts can be made because of gas entrapment. You're trying to get it to work and there's no way it's going to work. That's a pain in the neck, huh? Fine feeds, low permeability, no compacts can be made because of gas entrapment. Oh, you entrap the gas, but then the thing breaks apart. Problem number 1, fluidizes feed, intermittent feeding, reduces bulk density. Pressure and torque drop, air escapes out the bottom as well as the top. Fluidization collapses, high dense feed occurs and traps air and the process repeats. So this little jewel up here is a repeatable process. This is the So initially it's happening, then you have that, then you have this. Anyway, possible solution: use force feeder. Density fluctuations 1.2, 1.9, 1.7 to 1.9. Intermittent behavior causes damage to rollers, bearings, gears, and drives. Problem number 2, reduce roller capacity. Solution: use force feeder. Problem 3, no solution for fine feeds and low permeability. That means feed characteristics have to be changed. Coarsened feed particle size, increased permeability. Recycle crushed compacted material, need to experiment. Ideas for roller speed and permeability on air pressure. Yeah, you need ideas of roller speed and permeability on air pressure. Needs to be investigated. Strength of compacted sheets decrease with roller speed, less time at high speed to develop binding force. Trapped air does not limit coarse or moderately permeable materials. So if you're a variable feed type of plant where you don't know what type of feed you're going to be getting, you should pay attention to whether it's fines and permeable, not permeable, or coarse and permeable. Small range of low speeds are available for impermeable materials. Small range, low speeds are available. Air can escape with good designs, low flow rates, wide rollers are used. Plates are used to direct and contain the feed. Feeding is operated under pull vacuum. Other techniques, double rollers, pre-compaction, groove rollers. Some questions for you. I'm not into those. Let's go on here. Feeding rollers, roll briquetting, feeding, extrusion, and pelleting. Okay, this is a little bit unclear, but let's see if we can add some clarity of what's being discussed here. First, we're talking about feeder arrangements. Okay, you want uniform feed, it's required. So operation requires loss-free buildup of pressure in the nip, right, and minimize the leakage of materials. So design varies. Cheeks plates seal sides of the roller. You don't want stuff coming off the sides, right? And they allow pressure to be built up somewhat. Feeder base, obviously at the bottom of the feeder, it should prevent the material from overflowing top of the rollers. For free-flowing powders, a simple funnel can be used to feed the nip. Feed can also be adjusted with adjustable plates, baffles, tongues, or whatever you call them, which controls the opening to the feeding section. So you can have baffles, or you can have adjustable plates or scrapers. Or most powders with binders are not free-flowing. Right, that's a problem. Right, because they're not free-flowing, that means you may have to have a mechanical distribution along the top of your roller. Rotating arm spreads feeds across the opening. Pre-compaction is also a feeding option. Two rollers arrangement is common, one roller above the other. Okay. De-aeration is accomplished and the press capacity is improved. You can use gas chimneys or vacuum, also used for de-aeration. Force feeders are also possible if gravity is insufficient. Sometimes gravity doesn't work. Sometimes if the material is fluidized, gravity's obviously still working, but that's not important if it's fluidized. So force feeders are there's many designs for those. Okay, common screws in a row. Tapered screws may provide some de-aeration and densification, or pre-densification. You may have screw diameter effects. A screw diameter should not be larger than the nip at the end of the compaction zone. Should not be much larger than the nip at the upper end of the compaction zone. Too large a screw diameter results in too much feed, not immediately entering the compaction zone. So the end of the screw flight will cause a sine wave behavior in feeding when the screw flight comes by as opposed to not being there. Rounded, tapered, multi-flight screw, raising the screw reduces this effect. Screws used side by side, screw flights may or may not be overlapped. Overlapping will provide more uniform feed. You may have screw diameter effects which appear in the product, right? Screw diameter effects exist, but have not been well studied. Okay. That tends to be a detail. Moving on, roll briquetting. Now then, what would be interesting to see what we got here. Give you an idea of what's going on. We're going to make a briquette here. Here's Bob's. And we have our nip. We have the pre-densification, pre-compaction, nip region, release. Anyway, if filling and pressing process in a pocket is observed, it will be apparent that no phase of the motion are both halves of the pocket in full contact. In other words, what that just got done saying is these are not in full contact. At some point, it's open here at the top, and at the bottom, it's open. And in the middle of this, it's still open. It's open both places. So it will be apparent that at no phase of the movement are both halves of the pocket in full contact. At the start of the sequence, the pockets are in contact at the leading edge. So here's the leading edge here. They are open at the trailing edge. So this is the trailing edge. As the roller turns, the material in the leading edge compacts and densifies. So you fill this up, and then you have the approach of the closing around the compact, right, which compacts and densifies. As the pressure is applied, the material in the pocket is forced out of the pocket. The force exerted by the feed auger reduces or stops the backflow, but the shape and size of the pockets also have an effect on the briquette quality pocket wear, right? So it's claiming that you could potentially have a full briquette formed. However, this briquette hasn't been filled up yet with powder. And since there's air, there may be air trying to get out upward, which would prevent the solids from going in, which gives you this idea. You have oyster mouthing going on. You could potentially have cracks. You can also have webbing. This is the front edge. This is the leading edge. And the briquette, this is the briquette right here. That is this briquette, right? So I want you to go home or go wherever and get your bag of charcoal briquettes that you use. I want you to open the bag and examine it for the quality of briquettes that you have in your charcoal briquetting, right? And then I want you to eat some shredded wheat and see the little biscuits that are formed. And I want you to take a look at those biscuits. And then if you have pellets, fertilizer pellets or mulch pellets, take a look at those. So that's some ideas. Briquettes are not formed instantaneously. Phenomena varies along the entire length. Briquettes are hardly fault-free. Causes of faults are not understood. Faults include flashing or webbing around the perimeter at the lead, clamshelling, oyster mouthing, flashing a web, and distract from the appearance of briquettes. When I'm burning them on the fire for the barbecue, I don't care about the webbing and flashing. It could be a part where it's where I want to put the match. But anyway, here's some pictures for you. Special equipment may be needed to remove flashing and webbing. Well, put in the tumbler. Clamming, oyster mouthing, briquette does not close properly at the end, causing elastic recovery, air release. Can occur in leading edge too for very plastic materials. That's interesting. Briquettes front and backs experience different environments. Back end densities are higher. Studies are available on the mechanics involved and show the following. The material moves up out of the pocket as the pocket closes. So what that means is as this pocket closes here, the material goes up. Right there, it goes up. So let's see what happens. Moves up in the pocket. By the way, here's some material that has been briquetted. Kilowatt hours per ton, kilowatts per ton. Gives you kilowatts times time is energy. This is basically energy per ton. Pressure ranges, wow, look at that, pounds per square inch. That is high. 500 PSI. Without binder, with binder, and hot stuff. Stuff that's hot. Flue gas dust. Anyway. Sorry. Little axial flow occurs, variations in pocket change, strain patterns of the compact. Briquettes are typical pillows or almond shaped. Spherical briquettes break up. So it's hard to make one that's round because of high forces. Operating presses at low speed, operate presses at the lowest speed consistent with economics. Release and removal is important. Significant stress distributions change during the release. Adhesion between the pocket and the briquette can occur. Oh boy, that's a toughie there. Briquettes can expand during release if some damage can occur. It does not occur if it's inelastic. Will expand during release if elastic. Easy release depends upon release geometry and detailed geometry and properties of material. Release geometry, larger roller diameter to pocket length. Trailing edge closes before leading edge opens. It's interesting. Trailing edge closes before leading edge. That's for the larger rolls. Detailed geometry at no point on the pocket should be the normal different in the direction. Well, you got to sit there and reread that a little bit more. And why that is will be a mystery. We'll leave that one up to the mystery category. At no point on the pocket should the normal differ in the direction from the roll radius by more than 65 degrees. Now, there must be some really easy reason why that is true, but we're not have it at the present time. Briquettes need high shear strength. Pocket geometry may depend upon commercial requirements unrelated to production. Well, yes, pocket geometry is one of those fashion statements, probably. Pocket shape is not optimum. So, extrusion, my buddy extrusion. Extrusion advantages over die compression or die compaction. 12 time under pressure is higher for extrusion. Allows for densification and forming elastic materials and shaping hard brittle materials. So you're doing some crushing and grinding inside to smooth out brittle materials. Your creation fines. You may be changing the chemical nature or changing the elastic nature. Extrusion pressure is much higher than die pressures. Here's some extrudates. All right. Okay, some are from tabulating machines, catalyst pellets, primarily made by extrusion and cutting. There you go. So this is B, pellets. This is B. There's 3 figures to this. This is a B figure. Sorry about that. When binders are used, contents should be controlled. Too much liquid reduces densification, lowers agglomeration strength. Final product characteristics are mostly produced specific and may develop after extrusion. Are mostly specific and develop after extrusion. Anyway, discontinuous and continuous, obviously, uses a reciprocating ram. Peak pressures developed at each stroke. Materials forced through a die. Okay, pressure depends upon the geometry, the resistance of forcing through it, forcing material through the die, and the nature of material, plasticity, curing, structure, temperature. You have compression, early stages, the highest pressure, transport along the length. Variables are listed in the table. Let's take a look at the table. You have material characteristics, processing characteristics, and equipment characteristics. Plasticity and compressibility are material. Particle size is the shape, is process. And equipment might be die shape and wear. So you have, right? Geometry, energy statements, or process characteristics, maybe, and material characteristics. The three standard problems in design: material, how you're operating, and the geometry you're operating in. Okay. Variables, effective variables, not simple or uniform. Material inhomogeneous, inhomogeneities occur. Strength, density of extrude may change. Large differences in compaction behavior. If you're familiar with pump flow or pipe flow, okay, in pipe flow, you have this machine curve, or pump curve usually it's called, and then you have the mechanical energy system curve, mechanical energy system curve, or the system curve, or the mechanical energy balance. So you sort of like, if you remember your fluid mechanics from way back when, this is the screw characteristics. This is your pump right here. And your nozzle characteristics are here. That would be similar to your system curve for pipe flow. And where they intersect, where the system curve intersects with the pump curve, is the operating point, right? Which will tell you the pressure and the extrusion rate. Basically, you have volumetric flow rate here and pressure here. Right? Pressure times volumetric flow rate is actually the power. So if I take the mass pressure times the mass flow rate, I will eventually get power out of that. And where those two curves intersect is the operating point. So you ask the equipment supplier to give you this screw characteristic. You may not like, or she may not like to give it to you. You can ask for it. And that will certainly help you in understanding the operation of your machine. Because obviously you do not want to operate at low pressure over here. Although you have high flow rates, low pressures probably won't go through the dies. Up here you have low pressures and high flow rates. Excuse me, this won't go through the die. This will have no flow rates. Anyway, so it's an idea that you want to operate in the middle here, away from the extremes. And the nozzle characteristic you need to get a hold of as well. That represents your pumping system that you're pumping through. So this has complete analogy to mechanical energy balance, pump curve, and standard undergraduate fluid mechanics, which is rather sparsely covered. Operating point determines pressure and capacity. Like I said, similar to the MEB and pump curve intersection. Operating point becomes more difficult to determine For stage screws, special kneading, cooking, heating, transfer aerations. Now, if I was looking at this, I have a feed hopper here, and I want to actually mix. I want to put 3 or 4 things in here, and then extrude it. But I know a single screw extruder is a lousy mixer. So 2 options: I can go with a twin screw extruder, which mixes. But the screw will have mixing pins in them, or have the geometry change as you go down. Different flights, some back pumping actually, large contractions and expansions going on, anything to disrupt the flow. Or I could perhaps go with something called a co-kneader. Now, a co-kneader will set you back 3 million, 5 million. They're reset, for a decent size operation. Say I was making something like battery paste, right? You would want to use a co-kneader, reciprocates and rotates at the same time. It's single bore, maybe, but it's a very versatile machine, originally made by Baker Perkins, which has since changed to BP, which, I haven't checked lately, may have changed again. These business people are always running around merging to save us engineers. Anyway, so it's kind of interesting, this curve here. When I first saw this a long, long time ago, I said, oh, yeah, that's what that is. So anyway, operating points, the intersection of the die curve and the transport. I bet you have, maybe you do, maybe you don't. Depends whether you have this or not. Free zones, well, feed, transport, and extrusion. Single screw, poor mixers, screw design varies significantly. Usually want good mixing. Mixing pins, reverse flights, progressive closing flight, large diameter shaft, decreasing helix angles through mixing. This one, not so much, but mixing pins. Once you put air in something viscous, it's very difficult to get it out, right? I was working with some people. Well, I wasn't working for them, but they attended one of my courses, and they were making these lotions. It was in the cosmetic industry. They had these big batches of lotion, and they're completely aerated. And the aeration occurred as they were mixing the stuff, pulled in the air. And they had three days worth of time waiting for the air to eventually leave the tank so they could fill their bottles. If they filled their bottles with the air and the emulsions, the bottles after a while would be half full. And that would irritate their customers. So they had obviously what I would consider a problem, a processing problem that they created. And since they created it, they had to also get rid of it if they wanted to produce the product. Oftentimes, procedures contain in them steps that you do that create problems for you. So what's the logic in that? So there's no logic in that. So what happens is you readjust your procedure to prevent problems from happening. So their aeration that happened was they needed to do processing in an enclosed down tank where there is no liquid surface for entrainment of gas, an totally enclosed tank. And then they could have mixed their emulsions, and they wouldn't have to wait 3 days for a separation to occur. I threw some other things out there for them to think about. But it's pretty funny how bad off industry is about having procedures that they follow, and they follow them religiously for whatever reason, and they're just haven't been well thought out. at all. And there are many steps out there in the real world that do cause processing problems, which you then have to solve. It's unbelievable how much of that gets there. So the way you operate and get rid of flow air in the opposite direction, the material flow to escape. You want to have vents. Vacuum operations is a great idea. Staged operations is possible. First, aerate. First, don't let the air in. Operate under a vacuum. Second, have a vacuum. Complete, reliable, and removable air is most important to product quality. Air contains oxygen, and oxygen is a nasty material for destroying product quality. Product shape determined by die, typical short rod, 2 to 3 times in diameter. Pressure, material properties determine power use, capital. So what do we have? Pelleting machines. So what materials do we make pellets? Reason to pellet. If you take a look, handling, densification, reduce dust, elimination of fines, handling, control, and solubility. You want it porous. So all these are handling issues, right? So materials densified to some degree, forced through holes. Force exerted on the mass is relatively low. Binder plays an important part. Organic fibers, elastic, are typically made into pellets. Operations, let's go to the operations they're showing here. The cutter blades indicate that it has to roll past to cut it off. So this outer die is rotating. And inside there may be a similar rotating, co-rotating roller. And what you have is an amount of material sitting here waiting to be rolled over and squeezed through the die. There is material between the roller and the outer die ring and the inner roller. There's material in between there. You don't want the two metals to touch. It's not good. So you have this distance in here. I'm not sure how you would do that, but anyway, you have the no slip, pulls it in, squeezes it out. It may undergo some curing, and until it gets up here, it cuts it off. This is similarly, this is the roller inside. Here you have the cutter on the outside. Excuse me, here you have these two have the cutter on the outside, right? Here's the cutter outside, cutter outside, cutter outside. Interesting that you have, I just noticed this length to the cutter is a lot longer than this length. I wonder if that means there's two different products being performed, or products. The rolls are the same. I would hate to see different size rollers in there. Anyway, I just said a typical example of how industry changes things. I said that I wouldn't want to see two different size rollers in there. And I can envision somebody coming up with the fact that that's actually good for some processes. I don't know why right at the moment, but it's the fact that there's two different rollers in there, there would be a force imbalance, I'm sure. But anyway, you have the material fed in the nip, and the nip pushes the material through and cut off on the inner side. So you have two hollow rollers and the internal presses there. So what do we got up here? So we talked a little bit about that. Pressing tool rolls over the material, densifies, forces the material through holes. Not all the material is forced through at one time, obviously. Remaining material in the gap may expand after the tool passes. Okay. What that means is there's a residual layer here that may expand. You're feeding this from the top. This has to have a feed. And this is a plow that probably will push collect up the material and push it underneath the roller. So these devices have the rollers, the die jig, and then the plows in there as well, which aren't necessarily shown here. Gravity may act here if this is the way it sits. Lowest point gap remains between the die and the tool. Void metal-metal contact improves bonding in the feed. Dies may be flat, concave, convex. Roller matches die shape. Die-driven, pressing tool-driven, or both. Major differences in design is a tolerance for overfeeding. The feed is doubled. If the layer thickness is doubled, if the roller should not push material away. If not good, if material builds up in front of the roller and fills the entire machine cavity. Boy, that would be something, wouldn't it? Just overflows. Equipment can plug. Same problems occurs when you have fluctuating feed. Occurs if the machine is only temporarily overfed. Worst in concave machines. Concave die rings offer an advantage for processing elastic material. Longer and more slender nip allows more complete conversion of temporary elastic deformations into permanent plastic deformations. That's a real string of words. Roll force in the nips increases the gap and forces densification is gradual. Neither roll force nor resisting extrusion force is constant. Okay, let's see. Friction between roller, die, and material pulls feed into the nip. Area for densification and compression, that was the one. That was feed rolling in the nip. Low flow materials resistance may allow material to flow out of nip and reduce densification. May choke the machine. Obviously, what we're talking about is this one here, right, where there's a nip. See, this is the one with the nip. This is what you would call this is this behavior should be different than this behavior. This one has the potential of you having air, and this implies that there's no air in this feed. This implies air in the feed. This implies powder with air, and this implies some sort of paste, some sort of mud. So we got two different situations here, one with air in it, which causes problems, and one with sludge. So let's see, we covered that. Friction between roller and die material pulls feed into the nip for densification and compression. Smooth rollers may slip. May choke the machine. Binders, thickeners help, and lubricants may be harmful. Intermeshing teeth of mating roller and die surfaces will trap material and push through die holes. Intermeshing teeth is the gear pelletizer, right? You have a gear, intermeshing gear, and you turn that into a pelletizer. You make some clearance in there, and usually a positive displacement pump, there's very little clearances involved. There's no chance for backflow, but you take a positive displacement pump and take out some of the create voids in there for pellets or briquettes to form, and away you go. That's interesting. I haven't thought of using the positive displacement pump as a pelletizer. Obviously, if I use it as a pelletizer, I got to make sure the feed leaves the machine. If the feed doesn't leave the machine, then I ain't going to work. May yield products of uniform length. There you go. In regular pelleting machines with smooth rollers and dies, large amount of material can come through a few dies. Oh, geez. So you have a feed maldistribution. It's common. Feed maldistribution. I go to a roll agglomerator or roll one that creates the sheets. I have to worry about feeding the entire length of that roller, feeding it consistently. If I have a maldistribution of feed, I result in large extrudates through some die holes, and other die holes produce no or much shorter pellets. So I have a pellet size problem. Although feed's uniform output is non-uniform. So force resisting extrusion is great importance to product quality. No force, no compaction. Die holes must be structurally sound. Rarely are they straight single diameter holes. We spend a lot of time worrying about the shape of those dies, I tell you. L/D ratio determines the resistance of die and work done. That's just L/D is pipe flow again. A die hole is simply a pipe, you know, but not a single diameter pipe. It may be flared at the opening or at the back end, or both. Large entrances lead material to flow into the die, eliminates or minimizes clogging and matting of fibers. Now we got fibers in the mix, needed for high densification. Large tapered exit diameters control elastic spring back and avoid structural defects. So I have large entrances for flow in, and I have large tapered exit diameters control elastic spring back. So the die shape becomes sort of an interesting thing to think about. Perforated concave dies, it can't be too wide for structural reasons. Okay. Between the dies is a chunk of metal, and that could easily crack. Dies may be replaceable plates for particularly difficult tasks, high density, small diameter. Dies deteriorate by washing out inlet and discharge. Okay. Die life is determined by die diameter. Larger diameters last longer. Increased diameter until product quality becomes unacceptable. Die cooling is also possible to extend life. Product quality is determined by die size, shape of what you're trying to make, and density, shape of the die. Rollers are face hardened and can be rebuilt by overlay welding. Okay. 1, 3, and 5. I don't, what I always look for is 3-roll mills or 5-roll mills, die mills or extruding mills. I get the impression that 3 and 5, the forces balance out more evenly than even-numbered rollers, but that's purely my speculation. Anyway, let's see, adjustable plows, of course. Good idea. Scrapers, good idea. Can direct feed the material in front of the rollers. Rollers may be conical. Oh, there you go. For conical dies, there you go. Allows gaps to be adjusted. What that means is if you have a conical shape, okay, where you have a cone on the outside and a cone on the inside, the clearance of those two cones is a function of the height of the inner cone, or the height of the outer cone, or the height of both inner and outer cone. In other words, for a snug fit, the cones will touch. But if I drop one of them, the inner one, and raise the outer one, I've increased the clearance. That's kind of a cool idea you got to recognize about conical designs. 2 machines in series may improve operations. Flat die machines are useful for wet pastes and sticky materials. Materials may need to be treated. I haven't thought about that in a long time. Conical geometry lets you control clearances now. Okay, flat die machines useful for wet paste and sticky materials. Okay. See, flat die machines maybe the idea is perhaps you can scrape them easier. Scrape the surface easier. Materials may need to be pre-treated, conditioned, and post-treatment. Post-treatment often includes discharge to a dryer or cooler, heating, flushing with air or water, possibly coating, or by possibly coating, you produce an extrudate that may start to agglomerate on you. So the way you prevent agglomeration is you poison the surface. Example, donuts are covered with sugar coatings, primarily keep donuts from agglomerating. Powdered sugar is put on donuts and cookies to prevent them from agglomerating with each other. Clear plastic wrap for sandwiches have a coating of very fine silica to prevent agglomeration. Agglomeration is sitting around there everywhere. Anyway, afterwards, compacts must be handled carefully, right? After forming, handle like eggs, gently, gently. Rubber conveyor belts, properly designed chutes. Compactions are tumbled to remove excess like webbing, flashing. Weakened compacts, or, one way to recycle is you stress test your compacts, and the ones that break apart, you recycle. Many design arrangements can be developed, and simple concepts can lead to 5 to 15% improvements. Anyway, I finished that, and I hope it was understandable. And happy agglomeration to you. And again, thoroughly, this powder science technology book, great book. You can learn a lot. And also, again, as I said, I have said, this thing is an 800-page book. Okay, and it's a contributed chapter book. You have one expert and another expert and a third expert and an expert on experts. Just kidding. So you read the chapters that interest you, and you read 10 pages a night. And so you have a chapter that may be 100 pages long. In 10 nights, you got that sucker read. So that's why, self-improvement, instead of sitting there at night watching your wife or your husband read a novel, you can be improving yourself. I don't know what the good that would do to improve yourself, given the social conditions today. It seems like we won't comment further along those lines. Anyway, you all have happy agglomeration, and I hope you enjoyed this. Look, I got 5, 6, 7 editions. One of the interesting things about Perry's Handbook is the information may be correct and it may not be correct. That's true for all this, however. It's true for all this. Anyway, and obviously your experimental situation may be quite different. Now, what I would recommend, so if you're going to rely heavily on technical information, I would track down the authors. And I would even go back to the researchers that are doing the research in the area who wrote the technical papers, and I'd track them down, in which case I'd call them up and ask them. Anyway, I thoroughly enjoyed this, and please feel free. This is agglomeration, so my first 2 agglomeration, you should look at those if you're into tumbling agglomeration. The second one is tumbling agglomeration. You might try my drying course. Of course, that's be important in my size reduction courses. Anyway, I wish you a good day, and hope you have an enjoyable life. Thank you. And I will stop now.